Is it coming?
Yes, ma'am.
Yes, ma'am.
So we start the second part with the background now. Now we see that how cellular automata can prevent the fault attack. Okay, on grain cipher. So what we are doing that designing of the cellular automata stream cipher, but we'll see that mainly the how we can resist the attack that we discussed in the last session. Okay, I'll be coming later. Actually, this is one topic that almost last 8-9 years we are working, and why I'm showing this, even some more papers are also there. Again, till date, we are working here, 2019 also, and one the full paper we have sent to some journal. Mainly what I want to tell with this thing, that it's a very relevant topic, and challenges are there, and we can, many of us, we can join with this work, because we have not yet fulfilled or reached the target. Okay, so we started 2012, and still we are working here. So initially we are doing the attacks. Now later we saw that it is actually very much required to do a secure design. So this is the outline of my talk. I'll be giving introduction, objectives. I think this part we can omit, basic cellular automata. Then mainly I'll be coming the design part, okay, and the analysis part, security analysis part. Okay. So I already I mentioned that this is one type of the stream cipher is a kind of symmetric cipher, and what I was telling this is stream finalist. Actually, this is one competition. In the it was there, and finally the winners are these HC 128, Rabbit, Salsa, and Sosemanu. These are the 4 software based. That means they are well suited for software applications. And Grain version 1 and Mickey and Trivium. Mainly these 3 are the hardware based. And today's our main topic is Grain. Trivium is almost out, because we have done a lot of work at up, and other people have also done. So Trivium now people are not using. Grain and Mickey are actually they become standard. CA-based stream ciphers are actually what just now I show, that there are a number of CA-based stream ciphers, and Grain is a Grain-like, mainly the Grain, because Grain is the lightweight and it's very popular. So we have number of no cache, CAT30, CA stream, again Casca, Fresca. There are a lot of, as I show. This is only from our group. Again, other groups also, they have also worked. So from here, from in IIT Kharagpur, we have a lot of things, and so we understand that actually target has not been achieved. And always we try to with minimum cost, and like to maintain the lightweight and with the full security, how we can make it secure. So aim is actually secure against almost all known attacks. This is the things we are in. And vulnerable against fault attack. Fault attack is actually the one of the important things that we are thinking. So objective is to design a CA-based stream cipher secure against almost all known attacks, as well as particularly strong against fault attack. But this is one particular thing we are considering, but obviously this almost all known attacks. So you understand that this is one difficult task. So that earlier, what the last session, one question was there, that why linear, why non-linear? And there actually mainly here the answer lies. Another thing is that cost. That what hardware we can give, how much complexity we can afford. That is the thing. So this is actually with these 3 lines, actually lot of things, challenges are there. I think this part we can omit because now it is the last day of the workshop. All of we know this is the one flip-flop and combination logic. If it is a linear one-dimensional cellular automata, and we'll say this is one example of 5-cell. We know this rules depends on mainly the neighborhood relation, nothing else. So I'm just omitting this part. Okay. This is required because why I'm telling. Now, if we remember the grain, what was there? See, the structure is why I have told grain, because grain is here. It was NFSR, here it was LFSR, and this part it was a this combiner function or filter function. I told combiner. Now that structure we have taken, and see, instead of NFSR, we have taken the non-linear cellular automata. Simply LFSR is replaced by one linear cellular automata, and this part, this is actually we have taken some crypto-friendly functions like that. So this is say age, instead of only one function, again just we have chosen all those things by from our all past works, that we have taken some bend function, and here we have some, again some linear function, and together we have actually combined this thing. So this is our actually combiner. And see, this is the structure we have taken. This again, this is a NFSR. No, non-linear CA. Now N and L is non-linear CA, linear CA, non-linear CA, linear CA, and this is the thing. Now see the feedback. See the feedback thing. Again, what we have done? We have taken just we have taken tab bits from. Remember the earlier in grain it was 2 tab bits from non-linear NFSR or NFSR. We have few tab bits. Here you have some tab bits from L, and this is the feedback. Same. One thing is missing here. This is very, very important. If you remember, here there was one feedback to NFSR from LFSR and some of its bit. See, we have omitted this part. This is actually very important, I'm telling. So what we have seen that secure, earlier remember what the first session I have shown, that attack. That means how we have attacked. Then what we have seen that this feedback, and see if you remember, we have we injected fault in our model. We injected fault here, the non-linear part, and the existing attack or what that in the France people they did, they injected in the linear part. But finally, in both the things, that it is actually the whole key, the full key has been retrieved. Why? Because what is our research or our investigation shows, that the analysis we have done, that if this in between this feedback, actually if some fault injected here, then directly that impact of the fault or this fault, the effect that was induced in the non-linear part. Similarly, in our model, when we have fault we injected in the non-linear part, since some of the non-linear bits and the linear bits were fed, and in the pre-processing phase, see, it was again fed to LFSR. So actually the fault in the nonlinear part, actually it was affecting in linear also. And that's why the whole intermediate cipher and finally the key that we are getting. So from our attack, with the analysis, that what we have shown, that this feedback is directly inducing the faults. Either you induce the fault here, inject the fault here, it is induced here. If you inject the fault in nonlinear part, it will be inducing the linear part. But since it is the indirect effect, that's why in our case, that when that nonlinear portion we have injected fault, you remember, with much lesser number of faults, we are able to attack the thing. Okay. So now in our design, that's why what we have done, we have omitted these. We have this part, this feedback part, and then even if you inject the fault here, then directly it is not getting affected. Some indirect effect is there once it is a process, and then this thing. But before this thing is fed back, actually the filter function is there. That's why I told it is a filter function. So it is some bend function, and then again it is some linear function, that combiner is there. Similar thing will happen if fault is injected in nonlinear part, and then there is no direct thing, so linear part will also. Actually this is same. This is this nonlinear to linear portion is same, but linear to nonlinear, there is no direct path. So actually it is avoiding, or it is preventing this part with this. So this is small thing, but it is actually impact is big for security concept of point. Now what we have done is, already I mentioned, now see that linear block, a 128-bit maximum length linear hybrid CA. All of we know the cellular, this maximum length linear hybrid CA. So I've just given the polynomial. With this polynomial, I have taken, but this can actually be any primitive polynomial that I can, because 128-bit there will be number of maximum length CA I can get. So we have all experiments we have done with this polynomial. Okay, then nonlinear block we have taken. Here there are a lot of research that 128-bit maximum length nonlinear hybrid CA synthesized from the same linear CA we have taken. And here actually how we are getting this thing, that is another research, but I'm just giving the what type of CA I'm taking. So one maximum length non-linear hybrid cellular automata we are taking. Now it is a linear function. Remember, in our combiner function, then there is one HL and one is the bend function, H bend. So it uses 5 variables as inputs, 4 inputs taken from nonlinear part and 1 input from linear part. So we are taking here this thing. And nonlinear function H bend, it uses 8 variables as inputs, 2 inputs taken from N and 6 inputs from L. Earlier, remember, N took total 9, 2 from nonlinear part and 7 from linear part. But here we have actually taken different tap points and we have fed into this. Because we have kept. And we know the bend function is actually for cryptographic applications. It is used for its non-linearity, etc. And as I already mentioned, that linear is also required. So these are the different type of research we have done. That if we see that only non-linear function, then some attacks are actually happening. Okay, so that's why we have taken both linear and non-linear, and the combiner function is like that. So combiner function combines HL and HBent and finally produce this. This is very important. This is very, because if you give only linear function, then some attacks happen. If you give only, if you take only bent function, then it is actually finally, because this is the output. So finally it becomes a non-linear. And as I mentioned, that power attack actually affects more on non-linear function. If it is linear, power attack doesn't work. So somehow you have to do. So here, finally this becomes non-linear, but is linearity effect is there. So these are very small things. It seems it is very simple, but a lot of analysis is required to get the structure. Now this is the initialization phase. See, before we get the, it is just like a normal stream cipher. In general, the stream cipher concept is like that. That what we do, the before we get the final output or key stream, we iterate. This is an iterative type of thing, or feedback the output. So we use 128-bit key K and 128-bit initialization vector IV. Remember here actually the if you remember that in grain they took 128-bit key, but initialization vector IV they took 96 bits. And we have taken 128-bit because that remaining 128 minus 96, that for these bits actually they have taken 1. So again that can be actually guessed or something. Although this is a public thing, but it has some effects. So we have taken all random these things, and as usual the 128 bits of key are loaded, and that's nonlinear CA part is loaded with the key bits, 128-bit key bits, and initial vector is loaded in the linear C. The cipher is clocked for 128 cycles. See, here is some catch. If you remember, the grain was on 256 cycles. So immediately the half cycles we have done. Later we have reduced again some more. So this is 128 cycles without producing any key stream. That means this is called the pre-processing or the initialization. That means first this 128 cycle with this type of structure with no output. See, this is only feedback. That 128 cycles will be running like that and XORed with LFSR bits of both LNA. The initialization phase is made 2 times faster than that of grain 128. So this is one achievement. Always, and randomly I cannot do 128. First thing is that whether the if we cannot reduce anything like that, we cannot reduce what we want, because then it will be attacked. Some attacks can happen. It will not satisfy all the cryptographic properties. So actually this someone asked in the first session, this is very important, that initialization phase, how many cycles we want to run. These actually all the analysis, particularly the cryptanalysis we have to do, and then we have to determine that even our experience tells that it may happen some up to nth cycle we are getting good crypto properties. But if it is n-1, one less cycle, then property are totally different. It is not satisfying. So this is one thing you must keep in mind, that this is very important. And actually this is very mathematically it comes, because once running one cycle means, what earlier I was telling, this is nothing but all Boolean functions. So running one cycle means actually the Boolean functions are changing a lot. Similarly, we know our cellular automata, both linear and non-linear. If I just increase one cycle, then actually it is diffusing more, or it is increasing its radius. Okay, radius means that I'm telling that if it is 3 neighborhood or 5 neighborhood, then actually one cycle means it is spreading. So that's why that choosing cycle is very important. This is not the thing that 128 we randomly chosen. Not like that. I'm just reporting, but a lot of things we have done here. Now another big thing. See, these gap points. This from where we are taking the inputs to the combiner from linear part and the non-linear part. This is another thing. Actually, these 9 points mentioned in the grain, that 2 from in non-linear part and 7 from linear part. In our case also, we have taken. So these actually is very much selectively you have to take in. I'm telling why. See, these tap points that these are the tap points that it totally depends on that what type of nonlinear functions or linear functions they are there. If we can guess one, because there can be different type of attacks are there. So if some bit can be guessed and here it is such that on that bit not much effect is there with other bits, then actually it is good because you will not be getting the many number of bits. But if you get one bit, one output bit is such that the number of bits depend on that, then actually your probability is more to get the more number of bits. This type of very simple way I'm telling. There are many other effects, but just to give you the impression that why tab bits are important. Okay. I'm very simple way I'm telling, not that simple, but okay. This is overall idea. So that set of injection points denoted, this is one thing different. This is not tap points. This is the injection points, because here from the linear hybrid cellular automata, we are actually making that thing linear, non-linear hybrid cellular automata, both are of maximum length. There, actually, this is a different research. So I'm just telling the output that actually these are some injection points. Injection point means here we have actually some non-linearity we have injected, like some or of 2 bits or end of 2 bits, like that we have injected in these points. So these are 7, 1, 4, 5, 6, 7 injection points. A set of tab bits taken from the nonlinear block. So again, already I was discussing. See this B19, B39, 59, 7. These are not random at all, because it totally depends on your nonlinear block. As already I told that you have to choose the tab bits in such a way that so that if one of the bits is guessed, then also your things are secured. And that obviously depends on that what type of nonlinear cellular automata you are taking. That means what functions. Nonlinear cellular automata means what are it's every, what is the rule of each cell. Okay, so that means when you are tapping bits B19, that means this is nothing but a cell, one CSL. When we are using the cellular automata, then this 19th, if I think that this is a 19th cell, then the rule of 19th cell is very important. Similarly, the rule of 39 cell, 59th cell, 77th cell, these are actually you have to study. So this is, we are giving that, but it has a lot of analysis you have to do before you take this type of tab bits. You select the tab bits. Okay. Nonlinearity is injected in suitable positions of both sides of each tab bit to resist MS attack. See, this is again another thing. Actually every line has some analysis or thing. So this is one attack I'll be showing. This is called the Meyer and Staffelbach. We have given the name. Actually, this is Willy Meyer and Staffelbach, long ago they have shown that cellular automata rule 30. Actually, Wolfram proposed that rule 30 may be a very good rule to be used in cryptography, because rule 30 is a non-linear rule. Okay. Now XOR and OR. So now later in some Eurocrypt long back, I think I gave the paper 2004 or something, long back. Then just after Willy Meyer proposed that rule 30 may be a good cryptographic primitive, then Meyer and Staffelbach shows one attack that rule 30 can easily be reversed, can be that seed you can get. So that attack we have given the name as MS attack, Meyer and Staffelbach. So what we have done then, when we are telling the secure design, that means particularly when you are using cellular automata, then obviously this rule 30 and rule 30 is non-linear, Wolfram proposed. So many people initially we also tried to use the rule 30, and then we are getting that since rule 30 is attacked. So this is not a good choice. This is not a good choice. So what we have done, then this non-linearity when we have injected, so that time also we have considered the MS attack. That means selection of rules. And this selection of rules for non-linear cellular automata, this injecting point or injection point is very important. But that actually give you the expression or Boolean function of non-linear CA. So from that time only, we have actually the MS attack we have seen, and this is the first time actually we have, so far our knowledge goes, that no one that Meyer and Staffelbach when gave this rule 30 attack then we only applied this attack, or we employed this attack in our design. This is the first time, and I think this is very much relevant, because since it is cellular automata based, so cellular automata rule, attacks on cellular automata rule, that must be considered. Okay. Now in every segment of the nonlinear block containing 3 consecutive tab bits, we have maintained the injection points to resist MS attack. I'm just showing. Okay, I have tried at least with picture just to explain, because thing is very complex. Okay, see, I just with this simple example, at least I can give you some picture. See, this is some 128-bit state. See, see, this is my one state of linear has hybrid cellular automata with maximum length. Now I want to make it maximum length non-linear hybrid. We have algorithms for that. We have algorithms that will be following. Now for these algorithms, we have to inject non-linearity. Say some AND function will be injected. Now see, we have to these are the we have maintained, this is the actually the gap we have maintained, that, and this is one analysis we have done, that these with this 19, these are actually with some analysis that if it is 17-bit in bit, you see that initially it is 90, it actually totally reverse 19, 17, 13, 19. You can do the reverse thing also, because it is totally uniform structure. Then we saw that this is actually a very good structure that which can avoid your MS attack. And this is nothing but this, you have to, that injection point, there must be some gap. Actually, these are theoretically, it has been established that why this minimum gap is required. Okay, so that proof, etc., they are in the paper that I have shown the references. So here actually these theoretical proofs are there, that why minimum these things are required, otherwise it will be broken. Okay. Now these are my design rationale. since you remember, now you remember very simple things. There are 3 blocks. Linear part, I have used maximum period linear cellular automata. Why? Better randomness property than LFSR. I think now Shukanto was asking, so I'm trying to give the answer here only. So this is one maximum period linear cellular automata, and what Grain has done, the use the LFSR. So I have tried to explain better randomness property than LFSR, having a max length cycle, maximum length cycle, because LFSR always these are some small period because it is a shift. Actually, I should tell LFSR is one class of cellular automata, linear cellular automata. Cellular automata is the this is only one class, one small class. The universal thing is the cellular automata, and the LFSR is one part. So max period nonlinear cellular automata. That means again now this is maximum length nonlinear cellular automata. What just now I was showing. So having a maximum length cycle, no feedback path is required for linear to non. See, this is very important. Why this max period nonlinear cycle? If you remember, just to avoid the fault attack, we have omitted that XOR or feedback path from drain. But that was actually, that function was very good actually, it has some impact. So that impact we have to incorporate. So that's why, since no feedback path is required, no feedback path is required from linear to nonlinear, not required, we have omitted. And just to avoid the or to prevent the fault attack, so then my nonlinear portion must be enough competent to handle this thing. So that's why this is very important. I'll show that actually how to inject, or even not only that maximum period NHCA is sufficient, how we are getting that maximum period nonlinear CA. That means the different type of nonlinear CA that actually has effect on the attacks. That I'll be showing. That means not all maximum period NHCA can prevent the MS attack. This is one very nice observation we have got. I'll be showing. Then choice of HL and HBAND. This is for my combiner function. Actually, earlier was what other stream ciphers, particularly Grain, they have used only one function, one filter function. Now, what we have done, since BAND function is known, it is universally known as the best crypto function used in, even it is used in block cipher, that designing S box also. So that actually we have taken here. But Shumit was asking in the first half, actually this is one answer here, that see, this is not the full block cipher. This is only one sub function that is also used in designing block cipher S box. That actually we are taking here, HBAND, and along with one linear function. So that both are XOR and this has been taken. So that HBAND, this is a non-linearity. It actually gives the non-linearity. But then you will be telling why then you are taking HL. But it has a big problem. HBAND is non-linear, is nice, but it is not balanced. It is not balanced. So just to get the balanced, actually we have combined the linear, because all of we know that linear, particularly if you take the linear cellular automata type thing, it is very much balanced. So just to get the balancedness, we have done this thing. So a different way we can do. So everything you know, that the way we are designing, or the design ratio and all that, what we are choosing, main our aim is to prevent some attacks, or sometimes it has also, we have seen, just to avoid one attack, we invite another attack. This is also, so we must be very careful just when we are choosing our design parameters. So this is one thing. And occurrence of fault is equiprobable for all nonlinear terms in the bend function, because that is very, bend function is very important there in that way. So that's why we have chosen, or we have changed our combiner function. Okay. Now choice of output function, h dot. This is sum of hl dot and h bend dot. This is actually also different. This choice of output function, that also we have taken a different thing. So this is whenever it is a sum, you remember. If some of you have done cryptography, you know that XOR is a very good random thing. And always the final output, it actually gives you some type of masking, I'm telling. I'm just enough thing I'm telling. So this is also very, very important thing. So always you think, even if even one small XOR is not randomly taken, everything is analyzed and then only it has been taken. Every operation has some meaning. Okay. Even this choice of output, that sum we are taking, because sum means this is actually XOR, that means the final output is totally random. And this crypto primitive, any crypto primitive, whether it is authentication, hash, your encryption algorithms, that output must be a random thing. Okay. And this is strong attacks. Now, linear rules, all of we know that, because linear part we have taken the maximum length linear here, so I'm not telling this part, this is well known. Only these are the three neighborhood linear, so we have used only three neighborhood linear here, and with this combination of rules we have taken all in 9150 universal, but you can take a different rules. Actually this is why I am showing, because this may be a very good research in future, that whether not only 90 or 150, because choosing rules and uh, may give you the very good design. Not only the from hardware point of view, because hardware, that whether it will give you the yes, less costly structure, because these rules are nothing but neighborhood relation. So if I choose properly the neighbors or rule, then actually hardware will. Another thing is that not only hardware implementation, but rule means actually the Boolean function. So again, this Boolean function, and when particularly the cycles we are running, then the complex function that is generating, that also may be good. That's why this is one thing that people can do work here. Okay, so maximum period nonlinear cellular automata. This is with single nonlinearity injections, as I was telling. That not even if the linear hybrid cellular automata is maximum period, and then it will avoid the attack. It is not like that. So I'm giving one example. So this is one also a multiple maximum period nonlinear hybrid cellular automata. Okay, we have used this one existing algorithm. I'm not telling this because this is not the part of our this work. Oh, already this work is available, that from maximum length linear cellular automata, how to get maximum length non-linear cellular automata. So maximum 190, 150 maximum lengths here we have taken. And rule vector is 150, 150, 150, 90, 90. The 5 cell maximum length linear. Now we inject non-linearity. So actually we inject this is our linear CA function. Okay, this is 150, 150, 150, 90, 90. Okay. Now non-linearity is injected at position 2 on all the cells. How? This is x0 dot x4. So this is AND. This is the non-linearity. So we have injected, and see the state transition function are like that. The first one is not affected, it is simple XOR. linear. So this is x0, x1. So earlier what was there? See, earlier it was x0, x1, x2. Now this becomes x0 dot x4. This non-linearity. Then F2 is becomes because you are its effect. It depends on the linear neighbors, linearly with neighbors, and the neighbors are not becomes the non-linear property. So this becomes, this is actually, this line is coming from the algorithm, that how you are getting the non-linear thing. Just I'm showing the example, because how we are getting that is a different one. So this is my single injection point. What I want to tell, so this is injected nonlinear function is a single injection point. This is a single injection point. Then what we observed, okay, first we see some results. So synthesized CA is a maximum period CA. Synthesized NaCA cannot resist MS attack. See, this line is very important. That means, if remember this design, CA-based design, the nonlinear part is maximum length nonlinear cellular automata. So even if it is maximum length nonlinear cellular automata, but it cannot resist MS attack. What Williman and Stapleback has given. Okay, but see the cryptographic properties, nonlinearity, balancedness, and correlation immunity. Normally these are the properties all time we see. That it is not so bad, not so pure, and these are the iteration. Now we will get that why more cycles are required. See, iteration 1, this nonlinearity is like that. It is 2, it is 20442, 380. Now here it is moderately good 4, and see bitwise nonlinearity is also changing. And when more cycles we run, but the nonlinearity decreases. Why? No, this is only for, since I have taken only 5 bits here. Only I have taken 5 bits here. That's why, see, after these cycles, they are not getting this thing. Balancedness, because it is cellular automata, this is balancedness is fine. Balancedness we are getting. And this is something correlation immunity. Again, see, this correlation immunity is good for here, but it is actually changing. And again, since it is this part, it is not good because I have taken only 5 bits here. That's why. Okay, but otherwise it is thing. But main thing is it cannot resist MS attack. And since MS attack is, you remember, this is rule 30 attack. So since we are designing with cellular automata, so we have to consider MS attack. Otherwise, for other things, it is not required. So Meyer and Stapleback attack is a real threat for any CA-based cipher design. This is our observation, our achievement that we have given. And then proposed cipher is secure against MS attack, because if it is cellular automata based design, then rule 30, since it is rule 30 is a nonlinear proposed by Wolfram, that is attacked. So we have to show this thing. But just now the example I have shown, then it is not resisting actually the MS attack. Then demonomial test result shows that the cipher is strong against algebraic attack and correlation attack. So demonomial test we do, because CA means it has some inherent polynomials are there, and obviously with the cycles this polynomial actually changes with the complex thing, and then how the monomials we are getting, that is a very good measure. Again, for cellular automata, what we are showing that for cellular automata this type of measures are very, very important. And actually this is again some point where we can give comparison with LFSR also. Now secure against linear approximation always required, and strong against fault attack. This is what we started with this thing. Okay. So Meyer and Stapleback is a known print. Very briefly I am telling what is this thing with a simple thing I see. Just a minute. Okay. Just a minute. See here. So this Myers-Stapelbach attack is like that. So they are thinking that with a seed, they find that initial seed with after some cycle, whether the initial seed can be retrieved or not. This is the thing. Now, if we assume the initial seed is nothing but our key or some intermediate state of the cipher, because it is cellular automata based, then actually if MS attack holds, then actually you will be getting the intermediate states or key, which is actually a weakness or some attack or analysis I can take. So this is the thing. This is the thing. See, this is one seed and how it is evolving, and then with one bit whether we can retrieve, that means whether we can reverse the thing. Since rule 30 was non-linear, that's why Wolfram proposed that it may be the good thing. But what Meyer and Stapelbach shows that it is actually you can get the full seed here. Okay, and main concept I told, but now if some of you are interested, you can see the paper. Okay, this is Eurocrypt. You can give Meyer and Stapelbach, you will get the thing. Okay. Now see, resistance of nonlinear CA against MS attack. So the seed I want to take and give an output sequence up to the unicity distance and determine the seed. This is actually the thing that whether, and we saw that required time with the required time that it was, we are getting that thing. Now how to avoid? Then what we have done, remember that when we have synthesized the maximum length nonlinear cellular automata from linear cellular automata with single injection point, then actually it was not preventing the MS attack. Although it is this is actually maximum length. So what we have done now, instead of single injection, we are putting multiple injection points. See, multiple nonlinearity injections. Multiple nonlinearity. That means initially only we are putting it more nonlinear, because with single injection point, remember what we have shown the in nonlinearity. Nonlinearity, that it was nonlinear but not so good. Okay, here. And then with this result, we try to do a different thing. So what we do, removing restriction of single nonlinearity, we have put multiple nonlinearity. For multiple injection points, we consider the following criteria. These are all theoretical proofs are available in the paper. These I am giving only the result. Okay. So if some of you are interested, you can see the proofs. So what will be the gap? We have taken that these theorems are proved, and there must be at least 3 cells in between. These are the minimum gaps needed. Otherwise, we saw that actually it is broken, or that is not a very good choice for MNHCA. That maximum period nonlinear C. So with this multiple injection, now see, just I'm giving examples so that now instead of 5 cell, I have taken 9 cell, and similar things. These are my linear rules. And then we have, see, we have at least 2 points we have shown. We have here we are giving the non-linearity. Here also multiple. And see, there are in between there are 3 gaps. So 2 points we are injecting non-linearity. So we got the rules are like that. See, x0.x4, what earlier we have given, that is F1, and similarly F3 and no, it is F0, F1, F2, F3, F4, F5, F6. Okay, here also we have given something. I think it should be here, F5, 3, yes, F1 and F5. Okay, 3 gaps, x0.x4 and x4.x8. So these 2 are injected. These 2 as mainly these are the things. It is according to the algorithms that how you get the maximum length nonlinear CA from maximum length linear CA. With this algorithm, the other functions we are getting. So these are the 2 points we have injected. Now what we have seen, that nonlinearity increases more in multiple injections. Okay, so what we have seen, that nonlinearity, that these are the injection positions, and now again we have see the figure. Earlier it was 0, 1, 2, and now see the word nonlinearity with iterations we are getting with these. What are the big values we are getting? It's a just similar, because we started with one nonlinearity with 2 points, but we started only 2, and then this is the beauty of cellular automata. These LFSR cannot do this. Nonlinear LFSR never can do this thing, that with even 7 cycles and you will be getting this much of nonlinearity, that actually it is out of question. So with very lesser cost, we know that that is the novelty of CA, that only with a neighborhood relation, local neighborhood relation, and with cycles, that we are spreading the nonlinearity to other cells. What we have shown here also, that actually we have injected here one end and here one end, and finally we are getting, and then with the cycles, these also becomes very good. Okay. So this nonlinearity increases, and nonlinearity increases means that your security obviously is getting increased. And what we have seen, that now the MS attack is prevented with these nonlinearity, because simple. Remember the attacks, because whether, so simple thing is that whether you can reverse the thing. So if more nonlinear, then just after 1 or 2 cycles, it is not possible to go back, so that you will not be getting the P or the state, cipher state. So this is actually, I should tell earlier, but since I wanted to tell that thing, always the first thing is the linear cryptanalysis. So nonlinearity of the injection points increases with iterations, and the function h bent is not balanced. See, this is the point I already mentioned you. Otherwise, h bent is, cryptographic properties are good. It is nonlinear, this thing, but it increases nonlinearity, but it is not balanced. And if it is not balanced, then people can, that weakness people can exploit, and can some other attack can happen. So every time you have to see whether other cryptographic properties must be evolved, and the best approximation have biased these. So these are some experiments we have done, and we got this thing. So there are in total 256 linear approximations with this bias. So this is also this thing, how many you are getting. The function h bent has nonlinearity 120. Final combiner function h dot nonlinearity is this. See, this is the 120, and the final function after combining this h dot etc., we are getting 3840. That also increases with iterations. It can be claimed that the cipher is resistant against linear cryptanalysis. Okay. So this is a very simple way we have shown. Subresults. Now demonomial test. So one thing that because every cellular automata, this is actually very known, I'm not telling much, but this is, if it is a CA based design, and since CA is associated with a polynomial, so every iteration etc., that one polynomial is involved, and then that means every cycle, that how many monomials you are getting, and there are some good cryptographic point of view, that how many monomials are there actually. This is actually the chi-square test. This is very uniformly distributed, so all those results are there. So with this, it is actually every time we have to show that it is actually satisfying, and this is required. You will be asking why we are doing. So these actually demonomial test, if it satisfies, then faster growth of resiliency, resistance against correlation attack and algebraic attack. So cipher is strong against. So these are the 2 attacks actually we have guaranteed by using demonomial test. So a nonlinearity of this is linear approximation, nonlinear approximation, etc. Now fault location. See, I have not yet mentioned the fault thing because it is already there. see MS attack. Why I have given, why I was telling like that? Because what is our MS attack is? MS attack, whether we should get the initial seed, which is actually can be modeled as a key or the cipher state. Now, what was the fault attack principle? Fault attack principle is that if we can, any intermediate state, some register bit, I can change, flip to 1 or 0, then whether I can get this. So, why this MS attack is so relevant? Because see that what we have shown, remember, in the NHCA, we have injected the fault in the nonlinear part. Now here our nonlinear part is nothing but a nonlinear hybrid cellular automata. When it is by multiple injection we are getting, say this is my nonlinearity. This is my nonlinearity. So if I inject one fault and then after these many cycles, so why cycles are so important? Because these are actually with any value. So when you have injected one fault, that also is getting another key or another cipher state. Then also the nonlinearity, we are getting this thing. And with MS attack, what we have shown, that MS attack doesn't work means you will never get the initial seed. That means the initial seed is nothing but my key or the cipher state. So what is the relation? You will be telling why you have not told any fault. So fault means if 0 becomes 1 becomes 0. That means it is another state or another key. And whatever the key is, with this we have shown, whatever the state is, this is my nonlinearity we get. And with MS attack, what we show, that we cannot get the initial key. So that means that it is there. Okay, now I show the fault location. So now we actually introduced what I told. Now in the NHCA part, we have introduced the fault. That means, remember, we are successful in the grain model, that we injected the fault in nonlinear part, and then we got the full key. Now run the cipher for T cycles, set T equal to 10. We have done this experiment after injecting single bit fault. We have done this bit fault at the base point T. Base point T means just to mark, because after which cycle, remember that stream cipher or this grain type of cipher or this CA stream, I'm telling the general, it can be. So when it is running after some cycles, which is by base point T, that can be after 20th cycle, that can be after 30th cycle, like that. So here I have given the single bit fault. Then 13 bits of N can be obtained and no bits of L can be obtained at the base point T. So this is with our structure. Actually, variety of structure can be given. Here with the tap points that we have chosen, then what we have seen, that only 13 bits of N. Among 128 bits, only 13 bits we can obtain and no bits of L. That means that N means nonlinear part. Among the 128 bits of nonlinear CA, only we can get 13 bits, but among these 128 bits of linear, we cannot get any can be obtained at the base point T. See, since we have, remember, we have omitted that feedback part, there is no direct relation between L and T, linear and nonlinear CA, and then it is giving that. So now we have done this experiment we have made, that fault location, different, this is just few results we are showing, but you understand this is a fault simulation is a big one. So we have given these many places, fault location, and some iterations, because maximum 10 iterations we have given, because if it is more iterations, then it will be more difficult, or rather you can get more results, you can exploit. Then NHCA bits obtained is, these are the bits we can obtain with this fault location, again iteration, and these are actually continued, this thing. And we saw that at maximum 13 bits we can get, not more than that. So we cannot actually break the thing. Now we have quickly I tell, okay, just give me 1 or 2 minutes. So hardware implementation, we have full thing we have implemented in hardware because Cellular Automata is well suited for hardware. This is the another big advantage, all of you know. It has some analytical background, totally mathematical way it evolves. We can analyze all the properties, and again it is very useful for hardware implementation. So the cipher that I have told, this is general. So the cipher is implemented on Xilinx button 3, and this is one Casca is hardware efficient. This is one version, as I mentioned, Casca, Fresca, because the fault resilient. Fresca is actually fault resilient cipher. There we have shown only how it is preventing the fault attacks. This is again later version. So hardware efficient but vulnerable to MS attack. So this is vulnerable to MS attack because it was single injection point. So the proposed cipher is strong against known attacks. Efficiency of the proposed cipher is better than Grain 128 and no cache. No cache is another Cellular Automata based stream cipher. So that was there. So just quickly we see the comparison. So these are the number of 4 input LUTs, and see, even it is no cache or this Casca. These are this is one version of the cipher actually, and this is similar. This is 315, much lesser than this no cache, etc. Although it is better than security wise, it is better. But see, Grain 120 is only 27. It is very much lightweight, but it is fully attacked. Again, it is already we have shown that it is fault attack. So at the cost of some hardware that is not very much, not huge. At the cost of some attack, actually we are achieving the security. But this is the clock frequency is high. For Grain it is 178 megahertz. Ours is very big because it is for CA. We know the Cellular Automata is run since gigahertz. So this is one very good thing. Although hardware is more, but we are getting maximum cross frequency. Throughput is very good. Throughput is 236. So area is, see, it is 227, but here area is less because it is local neighborhood structure. It is very much compact design, very well suited for VLSI. That's why area is less. Throughput per area is also, see, throughput per area is very good. It is much better than Grain. Setup cycles are also half. For Grain it is 256. Setup cycles means the initialization, and our is half, 128. And non-linearity of the combiner function, this is actually here it is 61440 Grain, and see with this 3840, but don't think it is less because our cycles are involved here. So with this thing we are combiner function non-linearity, we are lesser, but still we are achieving the with the Cellular Automata properties, we are actually achieving other attacks. We are avoiding other attacks and almost all known attacks we have seen. That was our aim, but still, as I mentioned initially, still there are some challenges are still there, like this thing you can see, the combiner function, because only we have seen the Cellular Automata portion, linear, non-linear thing. This we can think better. Okay. So summary is that we introduced a new stream cipher design using Cellular Automata. First initialization, 128 cycles, secure against MS attack. To the best of our knowledge, this is very much this is the first time we have applied, and this attack is obviously every year we have to do. I repeatedly mention because that is mainly for Rule 30 proposed by Wolfram and broken by Willie Mayer, another cryptographer, big cryptographer and Stapleton. So we must show any size Cellular Automata based design. We must show this thing, and then use of maximum length nonlinear CA in place of NFSR, dropping of feedback function I mentioned from LFSR to NFSR, and use of rotational symmetric bend function make the cipher robust against fault attack. So these are the things we have achieved. So the design is now fault attack can be fully avoided with this design. These are some references, but still in internet you will be getting more and more. We have also many new papers that I have not mentioned here. Okay. Thank you.
Thank you once again.
I have taken 4 minutes extra.
Thank you once again, ma'am. Is there any questions?
30%.
Okay, I'm stop
Yes,
this thing, and if any questions. Okay, I actually there are many things, but I at least overview I have given, and there are many scopes are there. If some students are there are many scopes to work here. Actually. Particularly, I think cellular automata is very well suited, and we can give we can probably more challenges. Still, I have shown some challenges are there. That. Shukanto, now is it or your answer you have got?
Yeah. Still, I have a question, but maybe Sumit wants to ask something.
Okay.
Yes,
Okay.
I have 2 questions basically. In your function h bent, where you use h bent and hl, you are talking about that for balance property you have mixed up the function hl with h bent, and for balance property means the rules are balanced. For taking some rules.
No, balancedness is actually say when this is simple I'm giving. If cellular automata you run, say 128 bit 0101 you are getting, then you see in one particular bit how many zeros and ones you are getting. Balanced means if you get 50% 0 and 50% 1. Okay, not exactly, it can be plus minus 1, 2, then you call this is a very balanced. That means it is very important, balancedness is very important for cryptography, because if it is not, this is uniformly distributed actually, number of zeros and number of ones. In a particular bit, are you getting, say, you are getting 128 bit, a series of 128 thousands, and then you see some nth bit. Nth bit, if you see, then if it is 1000 cycles you have run, then it should be 500 zeros and 501. Then actually, the attacker is not getting any information. It is totally random. That 500 zero and 500. So this is called balanced. So bend function is otherwise it is very good cryptographic property. It is used in generating S-box, etc. But one big disadvantage is that it is not balanced. Bend function is like that. If it is say 5 bit, then x0 dot x1 plus x2 dot x3 plus x4 dot x5. This is bend function. This is the same.
Okay. Another question is, madam, for the maximal length where we use rule 90 and 150 for cryptanalysis purpose, but also we can get the maximal length using the complemented rule like 165 and 105. So if we use these rules for cryptanalysis purpose, then there is some advantage over to the 9150 or not?
No, I'm telling that you can do, but I already told that part. You can see may happen, but see, because not is not linear. So from crypto point of view, you may get thing, but parallelly you have to see. One complement means one not get you are extra using. So your hardware will be more. So always you have to see all the things. But what you were telling that you can do for some attack, it may resist some attacks. Okay, that every point what initially I started, every point you have to see like that. Yes, good question.
And I have one more question. Okay. That is for the in your approach you have taken that for the maximal length you have put the inject the nonlinearity in some position, then you get the nonlinear maximal length. But there is another some rules like if we use the like for a rule vector, some of the rules are linear and rest of the rules we have taken like rule 86, rule 89, rule 30, there maybe we can get a cycle close to maximum.
Yes, yes. This is also one thing you can do explore, but initially we have done that thing. So we thought that it will be a CA base, so it will be good. But thing is that non-linearity we are achieving here more. And another thing is hardware is very less. Because hardware you are giving only 2 AND gate. I have shown only multiple injections, only 2 AND gate I have given extra. And with these 2 AND gates, I have shown you that what big non-linearity we are getting. But this is also you can do, but initially we have done, and here also you have to do some balancing, that how many hardwares are required, or at the cost of hardware, how you can achieve that type of thing.
Okay. That means the cost of the hardware is much more.
Cost is more. Another thing is analysis is slightly tough, because you know that pure nonlinear CA, after some cycles it becomes a so complex thing, so it is very difficult to analyze. Rather pure linear CA, only 1 and 2 and it will be much. I have shown you that how it is coming, so it is easier to get the mathematical, but you can do this is. You can see and you can do some comparison, that how you are getting.
Thank you, ma'am. Thank you.
Okay.
Okay, I have a quick question.
Huh.
Yeah, I got the point regarding the advantage of cellular automata of what you have said. In case of other question is, in case of cellular automata, what we do local computation. It depends on neighbor, and based on that it computes. And in case of LFSR or NFSR, there's a feedback. Okay, so locality, constant in some cases it is not, violated. So can you have any advantage of using this LFSR, NFSR, what CA, due to this kind of feedback?
I got. So actually what you are telling, for some applications it may be some advantage. What I saw, we have done some work on scan chain based testing, etc. There it may be, but for crypto purposes there is no advantage. Actually it's a disadvantage if we use LFSR. Why I am telling, linear feedback shift register. So if you see, particularly if we, and if it is stream cipher type of thing, I have to run cycles, and then you will be getting totally relation. Well, pure correlation is there, because if you see 100 such patterns, 128 bit, 128, you will be getting this type of. So immediately attacker can break. Okay, so this is pure you are getting. If it is linear in this way shift, you will be seeing that one is getting shifted. Totally nice picture you will be seeing. One pattern, what we talk. So it is never, it becomes a random. And this cryptography, this randomness is very much required. And there are a lot of work. You say very old work. We have also, I have done it during my PhD. So it is universally CA is random. Actually, LFSR is only one small class of C. CA is the universal thing. There only one part is LFSR. LFSR comes under C. There is only one linear part, one linear combination of C. Okay. So in cryptography it is of no choice, but in scan chain type of thing it may happen where scan chain that shift is required. So that type of application it may be what you are telling. Here it is. Here actually no. It is a big disadvantage.
Okay, thank you, ma'am.
Okay.
Thank you, ma'am, for your nice presentation.
So any other questions or?
Any other questions? I think there is no more questions. Anyone?
Okay. So thank you all for the invitation.
Thank you.
Thank you, dear participants. Our next session, the last session actually, it will start at 2:30 p.m. The title of the topic is Computer Architecture, Cellular Automata and Security, which will be delivered by Chowdhury. Thank you. We'll again resume our session at 2:30 p.m.